So usually when we do these, it's to talk about a new product that we're about to launch. But we're going to do something a little bit different today, which is to talk about the research that went into a product. When we launched GPT 4.5, we thought people were going to like it. We were very proud of the model, but people liked it much more than we thought. People would said all kinds of things like, I never thought I was going to have this experience talking to a model. It's so different than GPT 4. It's way better in these ways that are either obvious or hard to explain or this or that. But there was like a lot of interest about what went into making GPT 4.5. So today, we have some of the key team that made GPT 4.5, and we're going to talk about it. We're going to talk about sort of like what went into it, what we learned, and just like what it takes to make a giant model like this. Actually, maybe we start with that. What does it take to make a giant model like this?
You go first.
A lot of people and a lot of time and a lot of compute.
Oh, maybe you guys should introduce yourselves. Alex, you want to start?
Sure. Yeah. Hi, I'm Alex. I work a lot on pre-training data. I also led pre-training ML for GPT 4.5.
I'm Amin Tutunchian. I am OpenAI's Chief System Architect. I oversee systems and networking broadly at OpenAI.
I'm Dan. I work on data efficiency and algorithms.
Yeah. Okay. So what goes into it?
Yeah. So I think we started this project basically 2 years ago or so. And we kind of knew that we had a big new cluster coming online, and we kind of saw this on the horizon, and we started doing a bunch of work to kind of convince ourselves of the features that we wanted to include in the run, doing a lot of large de-risking runs, building out a very long plan for this, and kind of across the full stack from systems, ML, everything. And yeah, it was a long story of execution for de-risking it and kind of preparing for the run before the run itself, which itself was a very large endeavor.
Yeah, I think it's a process that starts at the inception with a collaboration between the ML side and the system side and goes all the way to the time that we know what model precisely we want to train, and then it's starting the run process. In itself, with the pace that we are working at, and especially trying to make use of our most recent compute that is made available to us, it becomes something that is difficult to priorly plan perfectly. Mm-hmm. So we almost always go into a launch with a lot of unresolved issues and try to make forward progress throughout the run despite all the challenges. Basically add more compute, resolve all the issues that we priorly might not have anticipated despite all the projections that we had, both on the ML side and the system side, and try to basically close the gap between what we predicted should happen and what is happening. I think that is at a very high level and broadest stroke is the entirety of the process, and the tail end of it is the execution, which takes a lot of people, a lot of energy and momentum for a prolonged period of time to go through the training process.
How close do you feel like we were to what we expected to happen to what actually happened?
Usually at the beginning, I'm talking about the system side of it. We are usually far away from where we expected to be. And there is always a choice to delay the launch and basically defer until more and more issues are resolved, or launch early and try to basically figure it out as we go. It's always a balance of figuring out and not to delay the process unreasonably. But almost always there are issues that we don't necessarily know at the inception that we are going to run into. And the entirety of the process is try to handle the knowns to the extent that we can and have a plan for how the run should go. And as we make progress, just deal with the unknowns, which is the variability on, let's say, if a run is successful, how long it would take, and so on. How far away?
Well, yeah, I guess at the highest level, I guess with this project, we set out to do GPT 4.5, which means like 10x smarter than GPT 4. So that was sort of, I think, the initial goal starting like 2 years ago that we had set our sights on. And then there's a lot that kind of happened along the way of like, oh, we think, can we do better or worse? I think it was a very complicated road, but in the end, we got to a model that we feel hit this mark of 10x smarter than GPT-4 in terms of kind of the effective compute that we put into it.
Yeah, on the execution side of it, of course, initially it was far, far away from how long we thought that
It did take longer than we thought.
Yes, but I think the process is to try to shorten it to basically match what we were hoping for.
Two-part question about that. Why does going from, making up numbers here, 10,000 GPUs to 100,000 GPUs, why does that make the problem much harder?
A lot of issues, I do believe that issues that you observe at the scale, if you have a very keen eye, you would observe them at a smaller scale. It's not that they only manifest at a larger scale, but something that is a rare occurrence becomes something that is catastrophic at a scale, especially if you haven't anticipated it being
What are some of the kinds of things that have become catastrophic?
I mean, among those things is that I think is quite well known as issues with the infrastructure, the failure rates that you observe, the variety of failures that you observe, in both in terms of the types of failures and also the count itself. So we get to observe something that I'm sure the vendor hasn't observed because this is a large pool of samples, and we get to observe the entirety of the statistical distribution of a large pool of resources that we are executing on. The network fabric is always part of it, the individual accelerators are part of it, but at the end of the day, this is the beauty of it at the same time that almost everything needs to work as expected for the result to hold, and the job is to basically minimize that variance.
Second part of the question, obviously it's really hard, this is for all of you, really hard to do things at the edge of scale. So, even going, as we go off and do the next training run, even kind of crazier. But I've also noticed it gets much easier to go do things that are now no longer frontier. So it took like hundreds of people, almost all of OpenAI's effort to do GPT 4.5. If you guys could go pick whoever you wanted, what is the smallest team from OpenAI that could go retrain GPT 4 from scratch today with everything we know and have and all the systems work?
I think to get to a GPT-4 level model, it's probably on the order of maybe 5 to 10 people.
Yeah, we did it with that number of people with GPT-4. 4.5 was different in the sense that a lot of work streams, a lot more people come together, and it was a very different effort than GPT-4, I would say.
But now that we've done that work, I think like the stack, we've improved a lot. And like if you were to retrain, we kind of did this a little bit in the process of training GPT 4.5, we trained GPT 4.0, which was a GPT 4 caliber model that we retrained using a lot of the same stuff coming out of the GPT 4.5 research program. And I think doing that run itself actually took a much smaller number of people.
Right.
What about from your perspective, Dan? Or just sort of like, why is training big models hard?
I think doing anything new is hard. I think even just finding out that someone else did something, it becomes immensely easier because the hard part is having the conviction to do something in the first place. I feel like just the fact that something is possible is a huge cheat code that just makes it, Yeah. I mean, we're scaling 10x beyond what we did before with these GPT pre-training runs, and there's always new things that you find that are interesting that you couldn't have anticipated necessarily.
What do we need for the next 10x or 100x in pre-training scale?
Data efficiency.
What does that mean?
Easy answer.
Obviously, I know, but what does that mean?
So the transformer, the GPT, is spectacular at making productive use of data. It absorbs information. It compresses and generalizes to some degree, but its defining character, its signature is absorbing the information very efficiently with compute. But there's somewhat of a ceiling to how deep of an insight it can gain from the data. And so at some point, as the compute just keeps growing and growing and growing, and the data grows much less quickly, the data becomes the bottleneck of this standard paradigm. And it requires some algorithmic innovations to be able to spend more compute to learn more from the same amount of data.
What do you guys think we need to keep scaling in addition to that?
I think this answer is system side. I think even between different GPTs that we have trained, GPT 4.5 was the sheer volume of work that was required to, basically the changes that were required for us to make was a byproduct of the model specification. The same, we wouldn't have been able to train GPT 4.5 on the precise same stack as we did GPT-4. So let's say state management, our approach with state management changed. We had to scale to more compute, and that compute was not available as part of one cluster. We had to go to multi-cluster training. And imagine it's many, many different work streams like that have to come together in a short period of time for us to be able to do this, and for making another 10x jump, of course, and other issues that we previously knew that they do exist. It's just that it's a choice for expediting execution, that we skip them for this one. For the next one, we have to do it. There's no way around it. And it's always those choices that basically make the timeline of building the perfect system take much longer. So we are always compromising on what is the fastest way to get to this result. The systems is not an end in its own. The product, the thing that it produces is. So for the next 10x, for me, it would be, of course, fault tolerance. And a form of fault tolerance that we can co-design with the workload such that we don't have to worry the operational burden of keeping such a massive run going is not like our prior system. So I would argue that with our prior stack, 4.5 was at the edge of what we could keep up with.
Do you know what % of steps failed in the 4.5 run due to some component somewhere?
I actually don't have a number off the top of my head, but it is usually the way things work. This is a fascinating thing. There are issues that are early on in the lifetime of a new generation of hardware is not necessarily well understood or well studied. We start the process and we want to make forward progress in presence of such issues. Of course, the failure rates are quite significant earlier in the run. They're not necessarily, it could very well be that once we find the root cause and eliminate it, the total number of failures significantly drops. And this is often the case. It's just that we learn more. The infra, that is, some would call it cleanup of the infra or understanding fundamental issues about the infra. And the state improves significantly. But that earlier phase of execution is almost always quite painful because we are learning about what are the new failure modes in the new infrastructure while making forward progress. Of course, later on, the failure rates drop significantly. The uptime improves overall, and so on. But it's just a matter of prior. It is hard to predict what this early phase of a generation of infrastructure's lifetime failure risk would look like, and designing for the steadiest state might result in very poor availability earlier on in the process.
Obviously, reasoning models are a huge part of our future, and but if we were going to put this aside for a second and think about just how far we could go on classical pre-trained models, assuming we had unlimited GPUs and unlimited networking and unlimited power, but we were stuck with all of our current problems. The stuff still broke. We didn't figure out fault-tolerant training. We only had the data we have, whatever else. And we kind of use the convention of each major number of GPT as a 100x increment. How far could we go? Like GPT, what could we train with what we know today?
I think on
could we get to like a 5.5?
The ML and the algorithm side, I don't think there's like a clear limit that we've found. I think, I think we're just kind of scratching the surface of more data efficient algorithms and I think better ways to leverage the data that we have. It's very interesting because I think up until this rough point in time, like if you look even through GPT-4, we were largely just in a compute constrained environment. So that was kind of where all the research was going into, but now we're, in a very different kind of regime, starting with 4.5 for some aspects of the data, where we are much more data bound. So there's now a lot more excitement about this research.
It is a crazy update that I don't think the world has really grokked yet. I should pick a different word. That the world has understood yet. That we're no longer compute constrained on the best models we can produce. That's just that was so the world we lived in for so long. What was the most interesting ML thing we learned during the 4.5 training? that you want to share?
Oh gosh.
Or either of you.
I don't know what I could share.
In general terms, I think it is being off of the prediction and trying to figure out why we're off of the slope that we predicted to be on.
Yeah, I think that most surprising, maybe we can, yeah, I think one of the more surprising things that we found was just kind of how different aspects of what we were working on the ML side and what we put into the run scaled, and some things that did or didn't scale well that we kind of discovered through the process of training this model. It was, we learned a lot through this.
I'd say the two defining characteristics of the GPT paradigm has been that you can predict the test loss and it scales predictably, and magically lower test loss means greater intelligence in all these intangible, amazing, mysterious ways.
Are you a maximalist on that? Do you like fully believe that?
Well, I was going to say that one of the interesting things we found from 4.5, we tested it again, and the model has all of these incredibly nuanced abilities that were not in anyone's bingo card specifically. We just, like, the conviction was it's going to be more intelligent in ways that are really hard to characterize ahead of time. And then you see in the deployment, you see in the user satisfaction that it's smarter in all these very subtle ways. It has more common sense knowledge. It understands the nuance and context. And that's the magic that came out of the few extra bits of test loss. And I think that part of the scaling held up really well.
What was the most positive moment of the whole training run? What's the favorite memory? There's obviously lots of pain, but hopefully that's somewhat faded.
I do have one. But.
Yeah, I can go. So one that comes to mind for me, we worked a lot on the ML of the run during the run itself as well. And I think some of the changes that we made during the run had a quite good impact. I think maybe perhaps better than anticipated, and this was a pretty exciting moment for us.
Yeah, I think for me this was probably the biggest effort in terms of IC time during the run while we're building. I mean running things, we're building things in parallel. Of course. To get there faster, we are parallelizing work aggressively. And there is conviction that it will pay off. We will be past this performance cliff that makes the model essentially untrainable in terms of the time it would take to train. And there is a plan. Everybody is executing on it, but it's taking long. It's hard work, definitely harder than I imagined it would be. My projections were off. By how long it would take to basically get those issues resolved, and seeing the moment that the whole team, once a few of those issues got resolved, we got a big performance boost after.
I remember that.
Everybody you could sense that the energy changed. It's just that everybody feels excited and now more motivated to push everything through the end. It's fascinating.
Yeah,
part
you can
of
see the
mentality.
ETA on our status tracker.
ETA has constantly shifted from, let's say, 2 years to something tangible. Then the effect it has on the morale of the team and everything else, I think that was the beauty of it. The other part I would call out is the ML side of it didn't stop. The ML co-design part of this didn't stop at the launch at the launch time, and people tagged along. Issues that were left to say we'll figure it out later. People were actively working on it and shipping things that helped with execution time. And I think that is spirit of teamwork and basically not having team boundaries of I did my work, I pass it on to you, is something very powerful.
I was going to say, there's been a lot of focus on how the run itself was challenging and predictions were, but this is despite a tremendous amount of sophisticated planning.
Mm-hmm. Oh, this is, of course.
Do you want to say more about
you didn't
Oh, yeah, by far the most planning. Yeah, like I said, we started basically working on this project like a year before we even started training the run itself. And through this, we had a number of very large de-risking runs. We took a lot of care to kind of very carefully sequence all the changes that we wanted to put into it, starting from sort of like very high confidence, known good config. You can think like GPT-4, we really understand this setup from an ML perspective, and just layering things in and being very careful to very carefully study the scaling of all of the changes we're making. So it's not just good enough that we see some amount of win. We also want any win from any new feature to be like persistent across scale and not to be tapering off. Lots of things look good at small scale, don't look good at a large scale. So we had to be very, very paranoid through this process. And really, I think we continue to iterate on our scaling laws methodology. We learned a lot on that front through this de-risking process that's continuing to guide us for future GPTs.
I remember something I missed about another very fun moment. So this is the torch.sum bug. But imagine it is very unlikely that we launch a run and it doesn't have bugs. I mean, all sorts of bugs. It is just a given that, but we need to make forward progress. And we need to be sure that, okay, are we actually sure that this is on track and these bugs are not super negatively affecting the health of the run? While we are absolutely sure, we were initially very sure that there are bugs that are consequential. We have built a lot of systems around giving us visibility and ability to distinguish between is it a hardware fault, what type of hardware fault it is it some form of corruption, or is it some ML, potentially an ML bug, or something like races in our code. What happened was that we of course had a few open threads about all sorts of issues, that different symptoms, all correctness related issues. And at the end of the day, so of course we have found bugs, fixed them, and so on. We arrived at this point that we have multiple open threads. And there's a lot of thought around what is causing all these. Are they different bugs, or it's one bug and causing all of these? People went, around a table and say, everybody vote, which one do you think is the most probable cause of this bug? And the one that turned out to be the bug got the least votes. It's just that it is a torch.sum bug, a simple summation in upstream PyTorch. And everybody said, no.
What was the bug?
So the bug is this is funny because for the specific code path, we were triggering it. And for context, remember that we are mostly using Triton kernels. It's just that for some corner cases that, let's say, the ops don't matter much, we basically fall back to, it is okay to run torch ops. And our specific, the specific code path are data triggered for in the torch.sum function was basically had a bug. And it was only occurring very infrequently. It's just that it's data distribution dependent. And it was triggering, in good case, illegal memory accesses because it was computing some offsets and some bit of memory. The fun revelation at the end is that once somebody fixed the bug, our engineers figured out, oh, I found the bug. It is this line, it's torch.sum. Let's ship a fix and see if it fixes everything. It fixed all the outstanding bugs where they had seemingly distinct symptoms, and it was quite fun. And everybody, I think we were renaming Slack channels of multiple bug theory to single bug theory, and that was quite a lot of fun to basically. Okay.
When in the run did that happen? I can't remember now.
It was live from very early days of the run up until I think good portion of the run. I would say 40% in event.
Do you guys remember how someone found it?
I do remember that. I think it was in the list of, so imagine there is a sequence of kernel invocations, and the second one was the one that was triggering illegal memory accesses. And that was some very complicated kernel that we wrote. And of course, our team would suspect that there is a bug there. Obviously, there must be a bug there. And people, several very clever people, just line by line, everybody is looking at it. So a bug was found, but we rolled it out. Some of those issues disappeared, but not everything. And at some point, somebody was, in the list, torch.sum was the one feeding inputs to this kernel, one of the many inputs to this kernel. And somebody has started, one of our engineers started looking through the code and different code paths and say, oh, this very unlikely code path that probably most people don't hit, we do hit. And he said, okay, this line is buggy. Let's, of course, the only verification and validation we have for it is ship the change, observe if all the crashes disappear. And it did disappear. I think that was the validation we needed. So, but it was through, this is the thing. It's just that it's a crash at a very, very, a slow rate. It's 1 every 100 steps, 1 every 1,000 steps. And it's something very easy to dismiss. But it's just that we should not have that in the run as a discipline that we do have, and it's just not giving up on it is the story.
Alex, I understand what your life is like. I think most people can imagine it like leading up to like pushing go on the run. But after that happens, like what is your day-to-day like? Are you just like sitting there watching loss curves? Like how does it go?
Definitely a lot of watching loss curves. We all did a lot of that. No, I think past that, there's a variety of things still trying to work with systems to kind of get out improvements that we didn't get in on the co-design front before launch time. There's a lot of things that we try to continuously monitor of the run to see if anything is kind of trending like we're not expecting. So this is loss curves, but there's a bunch of other statistics that we can look at. And then, kind of working a bit towards like any other kinds of improvements we could do to the run as well from an ML perspective. So on the data front, it becomes less busy immediately once you click go, but otherwise there's still plenty to be done.
I think what we lean on for ML is a lot of correctness. Imagine there's a lot of noisy signal and you are at times reading tea leaves. It's just, is this healthy or not? Of course, if you wait long enough, you would know it. Was it healthy or not? It's just that the responsibility.
And how often are there false alarms there? Like how often are you like, oh, this is looking really bad, and then it's fine?
Pretty frequently, I think. Probably about half the time, maybe, because we're a paranoid bunch. So I think, if it wasn't half the time, we wouldn't be looking closely enough.
I have a short lightning round of questions.
Sure.
If you could have any one ML question answered before the next big run, what would you most like to know?
I think what algorithms we should employ with for limited data in certain domains is the main thing. It's a kind of vague question, or vague answer.
And if you could have any change to current hardware, you could have like a new kind of network invented or like a totally new chip architecture. Like what is the limiter on systems at this point? You don't get to like say, I want,
So this is a transport level network, transport level change. It's just that where there are faults that could be worked around at a different level than the application level, I would rather the network transport do its job and keep running and give me the available bandwidth without me worrying about it.
Is there anything promising on that front?
Yes, we can talk about
it. Okay, well, that's good at least. Two-part one for you, Dan. So on the data efficiency question, humans, for whatever other flaws we have about learning things, we seem unbelievably data efficient.
Yeah.
How far away is our very best algorithm currently from human level data
Really
efficiency?
hard to measure apples to apples. I think
just like vibes.
On language, astronomically far away.
100,000x.
It really
10,000x.
Something in that range. It depends on whether you count every bit of pixel information on the optical nerve, but we don't know algorithmically how to leverage that to be a human level at text. So I think algorithmically we're quite far away in an apples to apples.
And then part two is, do you think with the direction of our current approach, we will get to human level data efficiency, or is that just not going to happen and it doesn't matter?
Well, I think for decades, deep learning has been about compute efficiency. And what's magical besides the data and compute growth is that the algorithmic changes stack so well. you've got different people, different parts of the world finding this little trick that makes it 10% better and then 20% better, and they just keep stacking. There just hasn't yet been that kind of mobilization around data efficiency because it hasn't been worth it. Because when the data is there and you're compute limited, it's just not worth it. And so now we're entering a new stage of AI research where we'll be stacking data efficiency wins, 10% here, 20% there. And I think it would be a little foolish to make predictions about it hitting walls that I have no reason to predict a wall, but it's there. The brain certainly operates on different algorithmic principles than anything that's a small tweak around what we're doing. So we have to hedge a little bit there. But I think there's a lot of reason for optimism.
This next one's the same question for all three of you. Yes or no? Or you can add explanation too.
Yes.
Will humanity ever do a 10 million GPU or greater synchronous pre-training run?
I don't know if it'll exactly be a pre-training run, but I think there'll probably be some kind of training run.
Oh, there will
like
be
the
10
base
million
model.
GPU training.
Yeah. I don't know if it'll probably look totally different than what we're doing today, but there'll be something that is kind of in the spirit of unsupervised learning that is like at that scale. I think so.
I would call it semi-synchronous. And the scale of it, I hope so. I think it sounds very interesting.
Yeah.
You would call it semi-synchronous, you said?
Yes, I think not fully synchronous,
Yeah.
but it's just laws of nature. Can't bend it completely.
I think it's likely to be more decentralized than that. There'll definitely be 10 million GPUs working together on an AI system that is learning and doing things, but not all the parts of the brain won't necessarily all be talking to each other.
That makes sense. Can you say anything that we've learned or observed about how smarter and bigger pre-trained models correlate with how good a model is at learning and reasoning?
So I think what we've kind of observed is it is better pre-training and unsupervised learning. It just tends to lift kind of broad-based intelligence of the model and aid a lot in generalization, which we found to be like really complementary, I think, with reasoning, which can tend to be a little bit spikier, lumpier in terms of like where it's increasing intelligence. I think we found them to be good complements.
To go off on a little bit of a tangent, do any of you guys have like a intuition of, is it weird or is there anything to take away from the fact that pre-training seems to be so general across everything, and when we teach a model reasoning, we can get it so good only at one category of things?
Yeah, I don't know if it's the most. Yeah, I think it's interesting. I think it's kind of not surprising to see this out of pre-training when you're just look at what you're training with. When you construct like a training data set for pre-training, it's inherently very broad. We're targeting breadth and diversity. And I think it's kind of difficult to always get the same breadth when you talk about doing RL and having like environments that you can kind of cleanly get good reward signal out of and good environments out of.
I agree, but I think there's another factor that pre-training is essentially it's compressing the data, and compressing the data is about seeing connections between different things. It's about analogies. It's about abstractions, and reasoning is on a particular problem. There is a skill and a craft to thinking carefully, and thinking carefully can unlock many different kinds of problem solving in different domains. But there's something more learning at a more abstract level when you're compressing across domains in the way pre-training does.
That makes, I'm going to change my question for you in a second. I just thought of something else. What's going to limit us in terms of systems progress? Chips, processors, memory, network, or power? Like what will be the bottleneck of continuing to scale this up?
This is the beauty of systems, in that if we do co-design, the workload is adaptable to the infrastructure that you built. There is no statement that broadly network is a bottleneck, or memory bandwidth is a bottleneck, or the computer is a bottleneck. We have the option to basically shift, and even for the same specification of the model, we have the option of shifting resource demands to basically create a more balanced system. However, having said that, I think, let's say the pre-training answer is different than the inference answer and so on. but it never hurts to have more memory bandwidth. Yes, I think this is a hard question to answer and without qualification.
Speaking of that earlier point, how much do your teams work together on like the spec of the model as we get ready for the 4.5 run? Like how much is it? You're just like this.
Oh yeah, very closely. I mean, down to like the shapes of the map models that we want to be doing, making sure those are optimized well. But for this project, it was a much deeper collaboration going back to like I guess 6 or 9 months before the launch of the run, trying to do for some of the functionality we wanted to put into the run. And like aspects of what we needed to do to make 4.5 happen, we took on like a specific like very large de-risking run that was specifically focused on co-design with systems to make kind of the ML and the systems work together well at scale. So there I think it's the first time we put like such a large emphasis just on the co-design aspect. It was really key.
I think that was the first big scale effort that I remember, that it is not just about fine-tuning one aspect of it, is that fundamentally you want a property to hold system side. And that property doesn't emerge out of nowhere. You really need to steer the system to give you that property. So that co-design effort is something that formed the architecture and architectural elements that goes into the model, and somehow ties the system and ML side together. It's probably a property we would not prefer to have.
Yeah.
I would ideally want everything to be decoupled to basically give maximal room to each other. But at times things get tied together where you are really catering to the requirements of your infrastructure or how things should be. I mean, oftentimes it is, you really want to have a balanced system and balanced communication and a very symmetrical type of system. And you have the best knob we have at our disposal is all this co-design.
How close are we to the idealized Amin system? Or do you mean like fully happy? We have all the hardware we want. It works for what we know about ML.
We are nowhere near that. I think it is. We are nowhere near that. But it is fun. It is the practice of building systems is always about that you have an idealized view of how things should work, and it's just about reconciling the differences of that with what you have. I think we are not doing theory for the sake of, let's say, just talking about it, what we want it to be. We just want to make it happen and approximate that ideal to the degree that we can. So, to be honest, I think this is probably as exciting as it gets for systems. You get to really come up with hypothesis of what is a good system design. And take it from there and basically see the results in action very quickly. Things that previously one would say, this is an elegant system design. And we have to, just history will tell us if this is the right thing to do or the wrong thing to do. We have a lot of compute, we have a problem, we know the target, and just we go and see if our choices were correct or not.
How much is your team thinking about the sort of constraints of system design when they're trying to decide what's going to go into the run?
Yeah, I think it's a huge consideration for just doing pre-training runs at large. I think like since 4.5, a lot of the work on the architecture side, there's also kind of ongoing threads around further co-design, further places that we can design for future hardware, build together. I think there's been a lot of promising work already since then.
Okay, my changed question for you. Why does unsupervised learning work?
Compression. So the ideal intelligence is called Solomonoff induction. Basically, it's uncertain about what universe it's in, and it imagines it considers all possible universes, with simple ones more likely than less simple ones, and it's fully Bayesian. It keeps all of these possibilities in head and updates its views as it progresses, and you can approximate this by finding the shortest program that computes everything you've seen so far. And what we're doing with pre-training, or one way to think about what pre-training is doing, is it is compressing, it is trying to find the shortest program that explains all of the data that humans have produced so far as a way of approximating.
And why does looking at next token prediction do that?
It's actually a subtle question. There was a paradox, or somewhat of a paradox, in statistics for a long time. Why do deep networks generalize when they don't seem to compress? Normally in statistics, you have lots of data and you got small models. The models predict the data. Therefore, the models must have compressed and must have learned something. In pre-training, generally, the models are pretty gigantic and they scale roughly with the data. So it was always a question, are they actually compressing? Are they generalizing? And of course, there are critics who have said, well, it's just memorizing and interpolating, it's superficial. But there's a way of viewing pre-training such that you do see that it is a compressor in a different, unintuitive way. And basically, the idea is called prequential compression. And the idea is that the fact that it learns quickly during training means you can turn it into a great compressor. So even though the weights are big, the binary doesn't need to store the weights. The binary can pre-train from scratch to decompress. And so the fact that it's learning really, really quickly means that most of that data you can encode with very, very few bits. So basically, for a subtle reason, it really is quite a good compressor. And I think that is a pretty satisfying explanation for why it really does lead to intelligence.
You guys have anything to add?
No, it's great.
Thank you.
One thing, somewhat relatedly, that hasn't come up yet is the discipline of metrics. It's like the thing you get when you do these scaling laws and you do all the ML science is very dependent on the metric that you choose.
What do you mean?
Well, do you want to say?
Yeah, just talking about what test set you're evaluating your perplexity on. That's what you're referring
Well,
to.
even looking primarily at perplexity,
Oh, yes.
there's already some viewers might think we're looking at college tests or something.
Oh. Yeah. So yeah, I mean, do you want to explain perplexity then, Jans?
I think it's worth it.
Yeah, so it's very tempting to try to evaluate your model for intelligence on things that are legible to humans as tests. But if you do this, probably you're going to be favoring changes that make memorization easier at the cost of making systems actually smarter. Because almost every test that we have out there, there's something similar online. Like if you can actually train on the entire internet, tests become somewhat degenerate compared to tests for humans where they can't do that. And so the main approach in the field is to look at how much it compresses some held out data that's thought to be good data. And even then, if you're not careful about that held out data, it's too similar to your training data, changes to your training algorithm that make it memorize better will seem to make it smarter because it'll already know your test set.
And we don't want to just be measuring memorization.
Yeah, we don't
after
want that.
memorization. We're after generalization, and so out of distribution, generalization. So yeah, this is why I guess maybe what you're alluding to. So like the key test sets that we're looking at, we care a lot about them not being present in any degree, to the slightest degree, in our training set, because that kind of throws off all the way that we do our scaling laws. So yeah, this is a very key point.
What's our best thing for that?
So our internal code base, which we know is not out there. So yeah, it's a very good held out.
Has that held as our best thing across like many?
It's still the best thing, yeah.
It's remarkable. I mean, we joke that a model is its monorepo loss. Like everything else.
There's some incredibly meta recursive thing there.
But yeah, somehow you pre-train the model, it has a monorepo loss, and somehow this tells you so much about how it's going to behave down. It tells you a lot about how a philosophy grad student is going to find the nuances of its responses.
Yeah.
It's incredible.
It is incredible. Related to that, and sort of last question, in some sense, this whole effort, which was hugely expensive in terms of people and time and dollars and everything else, was an experiment to further validate that the scaling laws keep going.
Yeah.
And why, and turns out they do, and they probably keep going for a long time. I accept scaling laws, like I accept quantum mechanics or something, but they still don't, like, I still don't know why. Like, why should that be a property of the universe? So why are scaling laws a property of the universe?
Do you want to take
I can take a step. Well, the fact that more compression will lead to more intelligence, that has this very strong philosophical grounding. So the question is, why does training bigger models
Yes.
for longer give you more compression? And there are a lot of theories here. The one I like is that the relevant concepts are sort of sparse in the data of the world, and in particular, it's as a power law, so that the 100th most important concept appears in 1 out of 100 of the documents or whatever. So there's long tails.
Does that mean that if we make a perfect data set and figure out very data efficient algorithms, Amin can go home?
It means that there's potentially exponential compute wins on the table to be very sophisticated about your choice of data. But basically, when you just scoop up data passively, you're going to require 10xing your compute and your data to get the next constant number of things in that tail. And there's just, that tail keeps going, it's long, you can keep mining it. Although, as you alluded to, you can probably do a lot better.
I think that's a good place to leave it.